Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about how we can use coordination complexes to help increase the solubility of an ionic system. So we've already encountered many ionic solids when working through this material. One great example is aluminum trihydroxide. It can break apart into aluminum and to 3 hydroxide molecules. However, you may note this isn't exactly the most soluble species, so we wouldn't expect this reaction to proceed to any great extent. However, we've also seen that oxalate can help bind up free aluminum in solution and will make a much more stable aluminum oxalate complex with quite a large equilibrium constant, meaning this reaction is fairly favorable. We've seen in the past that one way to make a reaction more favorable is to pair an unfavorable reaction with a favorable one. So what would happen if I went ahead and tried to throw oxalate into my original aluminum hydroxide solution? Well, we can model this behavior by literally adding together these two reactions. The first thing you should do is look for any species that are shared by both reactions, one on the products and one on the reactants. In this case, both of these complexes have aluminum, so any aluminum generated by the hydroxide reaction should be immediately consumed by the oxalate species. And this generates a nice new reaction. Aluminum hydroxide plus oxalate gives the trioxalate aluminum aluminate 3 complex plus these 3 hydroxide groups. So now how do we go ahead and get the equilibrium constant? Well, if the reactions are simply added together, that means all we need to do is multiply our 2 reaction equilibrium constants by each other to get an overall equilibrium constant. So it is worth noting that this new equilibrium constant is still unfavorable, meaning that this aluminum hydroxide still doesn't want to dissolve, but it's much more likely to dissolve than it was originally, as this new equilibrium constant is still 16 orders of magnitude larger. Now let's go ahead and see what sort of implications this has on the solubility of the species. So what we're going to do is look at the solubility of our aluminum hydroxide solid in the presence of 0.1 molar oxalate. So what we can do is start by constructing an ice table. Now, one of the big things for this ice table is we're going to assume that the equilibrium constant is very small, because it is. And whenever we have a small equilibrium constant, this means that we're going to be able to approximate some of our x values. So let's go ahead and illustrate. So we're going to start with a concentration of oxalate and be generating some of our aluminum oxalate complex and the hydroxide. So we'll be consuming the oxalate and producing the hydroxide and the aluminum oxalate. However, the amount of oxalate being consumed will be fairly small. So I can go ahead and end up ignoring this and go ahead and look at exactly how much of the hydroxide and aluminum oxalate I end up producing. Now, one of the big things here is I'm able to use S for solubility instead of X, because what I'm really trying to figure out is the amount of moles of the aluminum hydroxide that I'm dissolving, which would show up here as a minus X. So let's go ahead and plug these new values into our equilibrium constant. So again, the oxalate concentration really won't change, so that will just show up as 0.1. The aluminum aluminum oxalate complex shows up as a single X value, and the hydroxide, that's the one that gets a little bit tricky, because we're producing 3 of them, but we then need to remember to cube the whole term. By combining all of these numerical values, we end up with our equilibrium constant being equal to 2.7 times 10 to the 4th times the solubility to the 4th power. So if I'm going to try and solve for solubility here, I now then need to divide both sides by my 27,000 term and take the quartic root, which we can simply do by raising the whole system to the 1/4 power. So when we go ahead and plug in our numbers and raise everything to the 1/4 power, we find that the solubility is equal to about 3.2 times 10 to the negative 6 molar. Now, this seems like a pretty low solubility. It is worth noting that this will generate a system with a pH of about 5, pH of about 9, a pOH of about 5. So this is going to be a fairly basic system, but it won't exactly be producing a ton of hydroxide or dissolving to a huge extent. However, one of the big things to keep in mind is if I looked at the original aluminum hydroxide, I'd expect the solubility to show up much closer to 3 times 10 to the negative 9th. So by adding in the oxalate, I was able to improve the solubility about 1,000-fold, which is no small thing. And this is a good trick for trying to increase the solubility of a lot of reluctant solids. However, it is worth noting that sometimes the best binding agent isn't going to be a chelating agent. It may just be an everyday average ligand. And it turns out there is a really good ligand to help dissolve aluminum hydroxide. It turns out it's actually hydroxide, because it turns out that if you combine aluminum with 4 hydroxide ligands, it generates tetrahydroxide aluminate 3, which actually has a very big formation constant. This is a very favorable ionic complex. And we can go ahead and also pair this with our original solubility reaction. And this will give us kind of a fun reaction here, because just as before, any aluminum produced by the dissolving aluminum hydroxide is then consumed in the production of our ionic complex. However, where we get a little bit fun here is that all 3 of those hydroxide ions that are produced are also consumed, leaving 1 hydroxide left on the reactant side. So when we add together these reactions, we end up with aluminum hydroxide plus a single hydroxide to give us our new complex. And to obtain our new equilibrium constant, we can do the same thing as before. Since we added the reactions, we'll multiply the formation constants, or the equilibrium constants, to give us a new modified solubility constant of 1.5 times 10 to the negative 3rd. Yep, that's a lot smaller than our original solubility. So we took a reluctantly soluble complex, and instead of by removing hydroxide, we actually did something a little unique that doesn't happen for most solids. We improved the solubility by adding a hydroxide. This is one of those cool features of aluminum that we made use of in the lab, where we were able to solidify hydroxides at low pHs, but as the pH increased, we actually were able to dissolve aluminum hydroxide by adding hydroxide. Now let's go ahead and try and determine the solubility of this species. But again, we should expect the solubility to increase a lot by having this much lower equilibrium constant. So in order to examine the solubility with one of these combined reactions, we need to know the concentration of the reagent that we added to the system, in this case, hydroxide. So let's go ahead and say that I'm going to try and examine the solubility of this species at a fairly high pH or fairly basic conditions. So let's go ahead and set the pH to 13, which will correspond to a system that's about 0.1 molar in hydroxide. So we can then construct our ice table, making use of the fact that we have 0.1 molar hydroxide and 0 molar of our resulting complex. We'll consume the hydroxide and produce the complex with, again, representing our X here as solubility, because we are indeed consuming the aluminum hydroxide. Now, we're going to assume that this equilibrium constant is fairly low. This approximation does start to break down a little bit here, but as we'll find out, it's good enough. Where we're going to assume that our hydroxide concentration stays relatively constant. In truth, you'd often add a buffer to keep that pH really fixed. Then we'll find that this will give a aluminum hydroxide complex concentration that's equal to the solubility. So we can then plug that into our equilibrium constant, and we have one of the easier expressions we've seen so far, where it's just going to be S divided by 0.1. If you want to get a more accurate quantification, you do this as S divided by 0.1 minus S. But when we solve for S, we find that our solubility is still fairly low, of about 1.5 times 10 to the negative fourth. So while we have increased the solubility of the system, it is worth noting there will still be a fair bit of, we are still relatively unlikely to be able to completely dissolve the system. But we did see that it is possible to enhance the solubility of a complex by being very selective of what free ligands that you end up throwing into solution. And this is a very good way of selectively dissolving any number of complexes. So next time, we're going to move on to looking at electrochemistry. It's time to play with some batteries. Until then, take care.